So, continuing our adventure of revisiting old stuff, we're going to be looking, starting off by looking at the calculation of different parts of formulas. So, let's start off with a real simple one. I don't remember. Was it this? Okay. All right, so percent composition, you can show the definition. If you remember, this was simply taking an entire compound and figuring out what percentage each element within the compound made up. Luckily, this skill was something that you had done before because finding a percentage was definitely a prereq for even making it into high school. So let's do an example real quick to remember the process. You can show the problem, please. So, you'll notice that, and of course y'all at home, I hope you have the slides in front of you or this doesn't work real well. The first question though is nickel 2 phosphate. So of course, being able to do your nomenclature is a prereq for a lot of questions, so this shouldn't make you struggle at all. So let's have somebody help me with nickel 2 phosphate. Let's head over to 4-1 there. Hooray. And let's go talk to person cluster 4, seat 1. That was exciting. Hey, nickel 2 phosphate, can you just tell me what the formula is? Not O, that's oxygen. Everybody okay with that translation? All right. So let's go through our percent composition process. Step 1 of finding the percentages of each element in that compound was to first find the molar mass. So let's just go through the slow process, or the long version, so that no one is left behind in any way. All right, so this compound is made up of nickel, phosphorus, and oxygen. We'll call it NEPO because it's cute. We need a number of each element in the compound. What I see are 3 nickels, 2 phosphoruses. Remember that subscript outside the parenthesis will multiply in. And then we're sitting there with our 8 oxygens. To find molar mass, we want to multiply those times the periodic table masses. So you can go ahead and reference what you see there. Nickel at 58.69. Phosphorus at 30.97. And then we get to use that magical number 16 for oxygen now.
That changed, right?
The AP rounds it to 16 from 15.999. Well, because they're only going 2 digits past the decimal in all molar masses. So the 9s round themselves up to 16.
What?
I'm sorry? So we will find those values together. All right, 3 times 58.69. I get 176.07. My phosphorus total 61.94. And then 128 for our oxygen. Is there any question on anything I've done so far in finding molar mass? Of course, we need to add those totals to get the molar mass. Can somebody yell that value at me clearly? What are the units of molar mass? No. AMU is average atomic mass. Grams per mole. Now, we're not going to run into questions anymore that just ask for molar mass. But we need that molar mass in order to find the percentage of each part of this compound. If you remember, percentages are found by part divided by whole times 100. So we'll do that for each of them. For example, nickel's total part in the compound was 176.07. If we divide that by the mass of the entire compound, 366.01, and multiply by 100, it'll give you his percentage. Please take a moment and find all three percentages, and we'll have one of y'all yell them out to me in a moment. Your notes will probably benefit by showing your work as often as possible. I understand the temptation on just doing it all on your calculator right now. But when you look back in your notes, it's usually handy to have all the work while you're remembering your process. Plus, one great thing about your AP exam is you get partial credit through all of the FR2s, so you're going to be trained to show as much stuff as you possibly can. So let's have somebody just read me all three of their percentages. Let's head on over to cluster 3, seat 6. Yeah, so nickel's percentage?
I got 48.11.
Make sure you have the percentage on there for your units. Phosphorus?
I got 16.9. I think 2.
Oxygen?
34.97.
Do we agree with these values?
Yes.
All right, and one way to generally check percent composition is to do what with your percentages? Add them up. They should equal 100% plus or minus 100th based on rounding. Of course, some of the follow-up questions you run into in pre-AP were things like, in nickel 2 phosphates, which element is present in the highest percentage? All right, to somebody guessing, oxygen might be an untrained guess because there's more of them, but of course, nickel makes up a higher percentage than oxygen. So those are some of the simple analytics. Questions? From now on, when you're pulling a number from the periodic table, yes. We have updated our table. Okay, let's change gears. If you'll go to the next slide, please. Oh, one job. Yeah, I'm just kidding. All right. Empirical molecular formulas was a slightly more involved process. But let's remind ourselves real quick on what the difference between the two are. If you remember, an empirical formula is one that's got the subscripts in their most reduced ratio. The type of compound that is always expressed empirically are ionic compounds, which is why when doing our shortcut on nomenclature, we make sure that our charges are reduced. A molecular formula is one that doesn't require its subscript ratio to be reduced, and this is what you find in molecules, which of course is any covalent compound. Keep in mind that even molecules might be in their most reduced form, like carbon monoxide is a 1-to-1 ratio of carbon to oxygens, and it's still a molecule. So understand that there's a vocab thing to be aware of there. But when finding a molecular formula, it doesn't require that reduction of subscripts. The process for finding these was fun. If you'll show the problem, please. So let's revisit how this works. Yeah, all of it. Yeah. So the compound that it's building here on the slide contains potassium, carbon, and oxygen. So let's just start off with knowing that we're dealing with those: potassium, carbon, and oxygen. What we don't know are the subscripts of the compound. Now, if you look at the question, it wants molecular. However, step 1 to finding molecular is to find empirical. So this question knocks out everything I could want you to remember. So let's remember how to find the empirical first. Step 1 was to divide the given percentages or masses by the PT values of the elements. So for the potassium here, it would therefore be 47 divided by the PT potassium mass of 39.10. We can set up the arithmetic for all of them. Carbon 14.5 divided by 12.01. And then oxygen 38.5 divided by 16. We'll find these values together. Get 1.2 for potassium. .21 for carbon. .41 for oxygen. What we found here is moles. All right, this is a conversion to the amount of moles of each element present. Does anyone remember the next step? Yes? You divide all 3 of those values by the smallest of those values. Yes?
Isn't there something I have to do with like 4 or 5 and you have to multiply by 2?
That's on the next step. So, let's do that. Now, if you're note-taking and you're like, I remember this, but I'm fuzzy, then instead of just dividing by 1.2 on all 3 of them, maybe out to the side, right, divide by smallest number here. All right, so that your notes are more useful to you that way. All right, so divide by 1.20 for each of them. And again, and people at home, please realize that if you want the long version of this lecture, it exists on YouTube. Cummings Chemistry, Empirical Molecular Formulas, it's somewhere. Click subscribe. I don't know. What?
There's only 2 classes that are going to be using these videos, right?
This year. You think I re-record every year? Those pre-AP videos y'all watched last year were recorded 3 years before I had you.
We're going to live on forever.
Especially today. You'll be surprised what I'm going to ask y'all to do in front of the camera today. Anyway, we'll get there in a moment. Oh, now, spoiler alert. Got a twist ending. Okay. If we do this, you're going to get 1, 1, and 2. Now, as Annalise brought up, it doesn't happen here, but you'll want to make yourself a note that there was something that could happen here. You don't have to write what I'm about to, because I don't want you to mess up your notes, or write it in the margin. But these values that you get after this step are the assigned empirical subscripts, unless one of them ends in 0.4, 0.5, or 0.6. For example, if one of them at this blue step here was 2.5, and then another one was 2, and another one was 1, if any of them end in 0.4, 0.5, 0.6, then we multiplied all of them by 2. in which case the empirical subscripts would become 542 if they were all multiplied by 2. So you've got to watch for that tenths place doing weird stuff. One thing that can happen, the questions usually aren't this mean to you, but does anyone know what would happen if one of them ended in a 0.3? What would you need to multiply them all by? 3. Remember, the whole point is to get the decimal number to equal a whole number-ish. All right, so how would you make 3.3 equal a whole number-ish? Well, if you multiply it by 3, it ends up equaling, well, 10 in that case. So anyhow, so that 0.3 might be something new for your brain, so make a note if you've got any concerns. We're not going to deal with our 0.7s and 0.2s. Okay, so these values here will be assigned to subscripts. It looks like we have an empirical of KCO2 by assigning those subscripts. That is an empirical formula, not what the question wants. So we need to continue the process. In order to now find the molecular, we need to first have the molar mass of the empirical. Now remember, you've already stolen the PT values of the elements, so you don't have to go look elsewhere again. My potassium, we're finding molar mass, is 39.10. My carbon, 12.01. And my oxygen, but there's 2 of them, is living there at 16 apiece. What did you get? 83.11 grams per mole is the molar mass of the empirical formula. If you look at the original question, there's one piece of information we have not yet used. Does anybody remember what we do with the mass that it's also giving us? You divide. Divide the given molecular mass by the empirical molar mass, and it will always give you a whole number. What whole number do you get here? You get a 2. That's the number that you multiply all the empirical subscripts by. Therefore, our final answer to the question is K2C2O4. Yep.
We're multiplied by 2 to get to the molar mass, right? Or like, why do we multiply by 2?
So if I divide, you see that given 162.22? I divided that by the molar mass of the empirical, and it gave me that number 2. Then I multiplied that 2 times these blue numbers to get these black numbers.
So how do you divide numbers?
By multiplying the quotient of the given molar mass by the empirical molar mass, it gave me the 2, and I multiplied it by each of those numbers. Hey, what's the name of that compound that we made? Nope. Let's be a grown-up about it.
What did you say?
What's it called? Potassium what? Chlorate's got chlorine in it. Oxalate. Yeah, it's potassium oxalate. Crazy, right? All right, next slide, please. The last topic of the day. Is a revisit of one of our old friends that's pretty important. If you remember, the reason that balancing equations exists is that the law of conservation of mass states that the total mass of your reactants must equal the total mass of your products. Oftentimes, when a reaction is first built and translated, the law is out of whack. So we add coefficients, the big numbers, in front of the different entities in order to balance the equation. Again, if you remember not being great at this, because I'm going to kind of look at it from an AP standpoint today instead of a pre-AP standpoint, then you'll be able to find extra practice on Schoology for free. Won't charge you a grade. However, we can also draw particulate diagrams to show reactions. The particulates have to do with, remember the images that we analyzed last week in the beakers with whether it was homogeneous or heterogeneous mixture and a solid liquid gas. We can draw pictures too, which we'll also do. So let's practice one. If you'll go ahead and switch the slide. Switch. So here is a fun problem. I'm just going to have one of you try to translate it for me. So let's see who we can pick on. Let's see who can tell me what to write. Let's go to cluster 2. That's where all the smart people are. Seat 1. Hey, 2-1. Can you do your best to translate, and you can do nomenclature if you've got the sharpness of what you see there? Well.
CU. CuCl2. Plus.
There's a glare up top here that my video people have trouble seeing.
And then the arrow.
The yield sign.
CUI. Plus.
Oh, KC, yeah. I thought you said CO. I was like, whoa, what happened? Plus what?
Plus beta. I don't know. Oh yeah. Okay.
I2. So, while translating, remember what we always want to be careful of is nomenclature. Of course, make sure that you understand the different type of compounds that show up so everything's written correctly. Remember that there are keywords for pluses and arrows. All right? And then the diatomics must be written correctly. Make sure that any free element that is a part of Brinkelhoff shows up with his 2, or everything just dies that moment. Now, an unbalanced reaction is always wrong. It's important to understand because a lot of times questions you run into don't specifically say balance this and then ask you a question. They assume that you know that an unbalanced reaction is wrong. Now, in pre-AP, you were trained that there's coefficients to fix this problem that we have. So you would make lists of the elements. You would duplicate the list under the product side. You would take account of the atoms on each side. 1, 2, 1, 1 here. And then 1, 1, 1, 3 here. And then your job was to make the lists match. Now, here's my hope for you. I don't make these lists when I'm balancing an equation. And it's not because I'm so much smarter than you. All right? Just through practice, you can get much quicker at this than having to do these elementary steps. Now, this is the only way you can solve it. There's nothing wrong with it. But to save time for longer problems, for those of y'all that are spending forever on Schoology already anyway, I'd like for you to be able to rationalize the answers instead of making the list, because most of y'all are brain equipped to do it. Now, I've given us a harder example on purpose to try to show you a more upper level way of looking at it, but really most of the equations that you're balancing, you can just do an eyeball comparison and figure it out. Again, you don't have to. Trying to push you the direction to not do the list. Now, if you were doing the list, you would add coefficients and update the lists as you do. But if I just look at this, what element's the most annoying element that's in this equation? Iodine is super annoying, all right? Now, when I'm training new chem students to do this, I always tell them to ignore split elements. See, he split. But you can get to the point where tackling them up front from a mathematical standpoint can be useful. All right? Like, here's what an untrained brain might think. How many iodines are there over there?
3.
So you might think, don't write this, that, well, if I put a 3 there, it would fix the iodine, but that would send you down a terrible road, because if you look at your other areas, that causes some problems. Like, you see chlorine here? Is there going to be an even or odd amount of chlorines on the left-hand side? No matter what. No matter what coefficient you put there, the amount of chlorines that you're going to have will be an even number. Therefore, you see how this would make there be 3 potassiums, which would require an odd number in front of that chlorine? It would be... Those are the kind of roads that I look for that before even starting, because I know that this, therefore, must also be an even number. So, again, through practice and not making your list, you'll get better at that. There's an easier even number, which is usually friendlier, not always right, but usually friendlier to hit, that we can get on both sides, and I would argue the number 4. Because I can make there be 4 iodines over there very easily. Where would I need to add a coefficient to make there be 4 total iodines on the product side? Right there. The moment you do that, there's a total of 4 iodines over there now. And really this becomes pretty simple. We've got 4 potassiums, so we would need 4 potassiums. All right. We've got 4 chlorines, so we would need there to be 4 chlorines. The coppers are now balanced. I would say it's a 2 to 4 to 2 to 4 to 1 mole ratio. If you remember to list a mole ratio, it's a simple listing of the coefficients in order. So we translated the reaction. All right, Kathleen did. She did awesome. We balanced the reaction. And now there's a ton of stuff it could ask us to do, but I want us to end class by looking at a particulate drawing of it. And here's where we could have some fun. I'm going to draw cards randomly, but you're going to walk in front of my camera. So you can say no. You can say I don't. So understand that if you walk up to the whiteboard to help me draw a particulate drawing in a moment, that you are consenting. They're consenting to being on YouTube, all right? If I draw your card and you want to use this as an excuse to just say no for a card draw, you have that power, all right? But let me show you what I mean. It's real easy. I don't want you to be scared of the concept part of it. One of the good things here is that it's not telling us what type of mixture that we're making, if it is a mixture, and it's not telling us states of matter, which means we've got some freedom in our drawings to simplify it. Most of the time when you run into a particulate drawing on the AP, they're always circles, but the circles have designs within them. I'm only pointing that out because if I do only circles and put designs within them with dry erase markers, it looks super ugly. So I'm going to use different shapes. But the AP, yeah, there are circles with different sizes, but they have a printer. They make it look pretty. So here's what we can do, though. We could say that all of the coppers, somebody give me a shape,
Square.
are going to be square. And we can say that all of the chlorines are going to be set a triangle. And we could say that all the potassiums are going to be a what? A circle, a rhombus. Come on. You're going to that's what's going to scare people out of coming up here. And we could say that all of the iodines are going to be a what?
Trapezoid.
A heart?
Draw a star.
Draw a realistic heart.
My daughters hate it when I draw hearts.
Gotta make it better.
Now, here's what we're going to do. Now, stop it. It's not that funny. All right. Now, if I were to draw 1 calcium chloride, just so no one's scared, if we keep the color scheme too, 1 calcium chloride would look like this.
Calcium. That's copper.
Oh, copper chloride, I'm sorry. All right. Now, I got a little creative with how my shapes attach, but do you see how it was 1 square and 2 triangles. All right, so that's all we're looking for. And I want to represent the entire reaction, though. All right, and we're going to do it on the other whiteboard, so we're going to do a little drag over here. Don't, just kidding. I don't have it. You didn't consent. Okay.
I consent.
Okay. Here we go. I'm gonna draw a card. You can say no if you want to, but we're just gonna go compound for compound. So here we go. The first person I invite to become famous is seat. Oh my God, cluster 2, seat 6.
Is it me? It's me.
All right. So hey, we're keeping the color scheme here. I'll bring all the markers over. We're keeping the color scheme,
I'll catch them.
and we're making the particulates match here. Now, here's what we're going to do. We're going to go from top to bottom. So we're going to go reactant, product, but you're only doing the first reactant.
It's hotter too. Okay, wait.
You can wave to the camera, but don't say anything inappropriate.
Hi.
Now I'm going to make a meme of you. Enjoy it.
Oh, thank you.
All right.
Okay.
So you're just doing right here.
What's the key? Oh, just right there. So
Yeah. So I want this part of the reaction at the very top of the board.
yes. Stop. What colors are those?
Red and the darker purple. So go up tall.
You go up tall?
The shapes are gonna be so
How tall?
bad.
Just at the
Take
top.
that back.
At the top.
I got it.
Keep going.
All right, so that's copper. That's one
Yes.
copper.
Yes.
All right, so it's CuCl2.
Oh, is it 2 CUs?
CuCl2.
Oh.
I feel like you're trying to really build your fame.
I'm really not.
No, Jacob, you
I
are.
spaced out thinking about how much I'll have fun being up here.
Yeah, I'm pretty sure that's
He'll watch it. He'll show it. Okay. Now,
They're really
but keep
nice.
in mind that there are how many of those?
There's 2, so I
There's
would
2
do
of
2.
them. There you go. Yay! There we are.
Oh my
All right.
gosh, they put eyes in
Smile for the camera.
Hi.
Okay, now put it away. All right. Now realize that I do want to show my plus sign between my reactants, and we're about to go to the other reactant. All right. So let's ask if person 4-5 would like to be famous. No. Okay. Let's go to person 1-6. Come on up. Go on up there. All right, so you are in charge of the potassium iodide.
I'm shaking.
You're stupid.
Take it back now.
Do I all touch them?
Yes, yeah, have them bonded together. In whatever creative way you want to.
Is that a 4?
Yeah, it's 4 Ki.
Make them out.
All right, so the crystal itself is just 1 K bonded to 1 I, but there's 4 of them.
Can I just write a
So
word?
revise. So revise your drawing here. You don't have to teach me. So erase 3 of your circles, and then bond an iodine to the potassium. There's no wrong way to do it. So mine would look. Yours will look instantly better than mine. So you're in good shape.
So you're both up.
Yeah, yeah.
That's crazy.
I mean,
both left-handed. That's crazy.
all right. Now, but how many of them are there?
4.
So rinse and repeat.
Okay, right next to it?
Yeah. Look how pretty chemistry is. All right, perfect. All right, wave to the people.
Okay.
Yay. Okay. And now we'll add our yield sign. All right. Hey, my next drawers, be careful because we have 3 more sections. So just don't go gigantor. I invite person 3-5 up. Reagan, would you like to? All right.
Look at his scary face.
Reagan, you're in charge of copper 1 iodide.
He's upset. He's ready to smack.
What colors are they?
We have red and blue turquoise. Yes, yes. Particulates are covered on the edges. And they could be in your FRQs. You could be asked to draw them.
What is that?
If you did that pre-response question.
Oh.
Actually, right.
Is that right?
Yeah, that's it. That's perfect. All right. Yeah, for those of y'all that are wondering what the heck we're doing, if an FRQ asks you to draw particulates, they will probably provide what the shapes are going to be. That they'll do this part for you, and it'll be something easy to draw. But this is not an unheard of question. All right. Let's invite person 4-5 again. It asked you twice. She said no twice. Okay.
They should ask me twice.
Let's head on over then to 2-4. Would you like to? No. Okay. Okay. All right. We're gonna run out of time because nobody likes to
I'll do it.
play. All right. Let's go over to 4-3. All right. Come on up. All right. 4-3. We're sitting here with 3 minutes, y'all. We're gonna try to get our pictures done. All right. You're gonna be in charge of potassium chloride. Oh, I'm sorry. Tried to kill you. Said it on video. Now they all know. I dropped another one.
You should point at the camera.
Now you will. Here, don't show. Yes, yes, yes.
It's a rock.
Don't shuffle. Be nice. Oh, that was the question? Oh, I'm sorry. I thought you were asking to head out. What's up? I got it.
Just saying, I just want to Mr. Cummings video.
How'd she do? Great.
Good.
Great. All right. Hey, let's see if we can finish. Person. We have 7.
You give at 35.
Quit putting your stuff away then. Y'all are the mean ones.
Me?
Yes, that's very mean. It hurts my feelings. Okay.
That's so rude.
All right. If I get a no here, I'm just going to draw it. But let's go over to 5-6 Aspen. Would you like to? All right, Aspen. Come on up. Aspen, you're in charge of iodine.
Yeah, up and go up and.
You're famous.
I can't wait.
Can't wait to screen record this.
I hate you.
I'm gonna go. I see this
kidding.
thing. See, you have to put stack. It's also a screen record.
All right, and they're bonded. Like make them hold hands at least.
Aww.
How cute. 2 hearts holding hands.
Oh wow, you got super literal. Cool.
It's pretty realistic.
All right. So don't give your particulates hands.
Oh, adorable.
But
Look at that.
No.
Oh, I thought you were going to.
But here is a pictorial representation of the exact same reaction. Now, I want to point out that this question could have been harder, though, if it would have given you states of matter and said it was happening in a beaker. All right, because remember, we can show states of matter and particulates based on the way that we draw them. Remember, solids are along the bottom and organized. Liquids are along the bottom but slightly disorganized. Gases are floating around near the top. How would you show if a particulate was a heterozygous mixture? Heterogeneous mixture. I love biology too.
Gross.
What about the line?
It has to be slightly further.
The ability to draw one. Remember, if you can draw a line separating the components in there, even if it's slightly curved, that would show that it's heterogeneous. Are there any questions on this review? Tomorrow, our very last topic, you don't have to switch it, will be our favorite topic from pre-AP. We'll be revisiting stoichiometry. Y'all have a good day. Wait for the bell.
Chemical Rooster signing out.
Yeah, they're here.